So my name is Mohammed Noor. I work at Citadel. I've been using KDB for about 14 years, with a number of people actually here in the crowd. I'm excited to talk to you about our journey of integrating PyKX into our KDB framework at Citadel. I'm going to be joined with by Oliver shortly, who'll talk you through some of the more technical detail of it. Those last two. So I'll start off with just giving a bit of background on how Citadel uses KDB. It's a little different to how other firms use KDB. So we introduced KDB for about 6 years ago at Citadel. We were brought in to make QR lives easier, as many firms do with KDB, to provide a central platform for QRs to easily access data in a consistent way. So we built that out, and very quickly after that, people liked what we were doing, and they asked us to build more components on top. We very quickly built out a KDB framework, which allowed you to use standard things that you do with KDB, so your standard time series database. We put a lot of focus into real-time event processing, because that was the kind of direction that we saw that people were going in at Citadel. So at the moment, so that was about 6 years ago, so we built this out. We made it super easy for you to take KDB, take our libraries, and write a bit of Q code and build out fairly intricate real-time event processing systems in KDB. Where we stand today is we've got about between 15 or 20 projects across the whole organization doing very disparate things with KDB. Some of them your traditional market data, event processing, transaction event processing, but also some more interesting, slightly quirky use cases as well. So in terms of real-time event processing, I think most of the people in the room probably know what real-time event processing is, but let me just lay a bit more foundation. So we're seeing increasingly everything is driven by data. And the previous world of trying to figure out what your data looks like, what analytics you can draw at T+1, the day after, or even after a few hours is way too slow in the financial industry. So quite often you build systems to take your real-time streaming data and draw real-time insights to it. The next step after that is do predictive insights on top of it. You then take that information and you take some kind of action off the back of that. That could be, make a trade, stop trading, or more intricate things of, generate an alert around, infra alerts around capacity. And quite often you find that in certain use cases, depending on how the system is being built and how it's being used, batch operations can be quite inefficient for operating on large volumes of data. Generally, having the incremental streaming approach is more efficient. So an actual real-time use case of this is to do with market data anomaly. Anyone who's in finance dealing with market data in real time, you generally build a system like this, which looking at market data, it's not always perfect. There's always going to be some kind of issue from time to time with the market data. So in a system like this, typical inputs are going to be obviously your real-time market data, be it trades, quotes, NBBO. You also need some kind of historic reference for what prices generally, how they generally trend. You also need static data around that market data. That could be instrument, corporate action information. It could be tick sizes. These are kind of like the expected anomalies or data changes that you anticipate are going to occur. You also kind of generally want to feedback some kind of operator feedback where maybe you generate an alert because of some kind of condition, and you need to recalibrate that in real time without doing a release. So have some kind of operator feedback feeding in. Then you need to actually do some logic on top. There's different approaches you can take depending on the problem space you're dealing with. For market data, there's generally 3 different approaches. I'd say you can have a very simple rules-based engine, which is looking for certain conditions to break and generating alert of that. You can have a statistical approach, which is looking at variances of prices over time. And increasingly, you're seeing, depending on the problem domain, more ML-type solutions where you calibrate a model and using the model to look for anomalies in real time. Once you have your signal, there's various actions you can take. Most typically, you'll generate an alert that goes out to some kind of system, be it Datadog or PagerDuty or in some places emails. The next thing you do after that is you may want to feed that into another system. That will take some kind of action off the back of that in an automated way. And the third thing you may want to do is when these systems get somewhat complex, and they generate alerts left, right, and center, you may want to actually go and figure out what is the system doing. So you may want to get a real-time diagnostic feed of data going out to a UI. That's generally the pattern that real-time event processing systems take. So if you're building real-time event processing in KDB, let me start off with the reference architecture and like kind of the shape it takes and how we kind of think about it at Citadel. So we will start with the reference architecture. Everyone in the room should hopefully be familiar with this. Who's on KDB, you've got the ticker plant and RDB as real-time components. With the ticker plant, you've got a journal file, which is there for recovery, and your RDB just has an in-memory state of all the data for the day. The prototypical example of doing some kind of more interesting analytics on top with KDB is you generate a real-time event processor or a CEP that looks very much like an RDB, but it has some more interesting logic on the update callback. So with RDB, it's a very simple, you insert it into the in-memory table. In this case, you may do something more interesting, a typical one would like calculating VWAP. So you'll do that, and that data will be available in that process to consume for downstream clients. There's two kind of limitations here of this model. One is if you have a number of these event processes built out, the recovery time in the case of failure can be quite large. The journal file is on this file. You need to be able to share that across multiple components or multiple recovery components. You need to be able to access it locally. So you're kind of constrained by either having it all on one physical machine, or you need to have some kind of shared file system or some way to synchronize the journal file if you go beyond one machine. The other limitation is if you're recovering the state of your event processes, they need to read through the whole journal. There are approaches to allow chunking up the journal, but in the basic example, you'll normally have to go through the whole journal to recover your state. And most typically, you only really care about the most recent data. So those are two kind of limitations you have with this kind of architecture. The way we kind of implemented it at Citadel is we have the event processes able to recover from the RDB directly. So that does introduce a limitation that you need your RDB to recover first before you can start recovering the state of your event processes. But as soon as you have a number of this scales much, much better for two reasons. One is it's generally in memory, so you can access it from memory, which is much, much faster than disk. And the second reason is you can randomly access into it. So you can write a very simple query to get the last value cache rather than having to go through all the data. And also, it's available over TCP, so anywhere you've got TCP connection between two boxes, you can run one of these event processes. The other key thing that we changed is we can now also chain these event processes together to create a directed acyclic graph of computation. So instead of having a single layer of computation, you can kind of take your logic, break it up into logical components, have microservices dealing with each component. And as part of that, you also need to take a recovery and have your components able to recover from other event processes. And that's very easy in KDB because all you do is when you generate some data, you publish it out, you just keep a copy in memory, just upsert it into a table in memory. So that's kind of the logical architecture that we have for our real-time event processes. And this is a really powerful construct because what you can do is you can quickly create dynamic graphs for real-time event processing. So what we have here is an example of calculating order notional off the back of some data. So we've got two top-level CEPs. So you've got the order state event processor. What that's doing is taking, as a very simple example, it's taking fixed messages, order news, order cancel, order amends, and generating a consistent state on top of that for your orders. And that's its responsibility, and it feeds out a very clean feed of order state information. We also have the reference price calculation engine, and again, this is doing something very similar, but for market data. It's generating a clean reference price. That's its only responsibility is just generate that price feed. You don't need to have that in multiple components in your graph. So that's the top level. You've got the order state and you've got the reference price. And then below that, you have order notional being calculated, which is a very simple operation, taking your orders and your market data, multiplying the two things, and generating an order notional feed. As another example, once you have these core constructs in place, you can add on additional layers, doing additional things below. So we've got an example here where we decided the DQM, the data quality monitoring of the reference price stream, it's maybe too compute heavy to put in line with the reference price component. It'll slow it down. So you can always layer it below it. And it's going to be running on a different core, maybe on a different machine, and generating alerts off it. So with these kind of like building blocks, you can go even further and generate more intricate graphs. So I think probably in the largest graph that we have at Citadel, it's probably in the order of maybe 80 to 100 odd nodes. And it's processing in the order of maybe a few trillion events per day during the trading session. So once you have this, and you show it to people, the first thing they say is that's pretty powerful. So what you find is there's two main constructs that people want to take on from this. One is with the libraries that we've developed, to actually create one of these real-time event processes that just sit anywhere in the graph. It's in order of 3 or 4 lines of Q code. It's not that significant. All the boilerplate is taken care of for you. All the recovery logic, it's all there already. So all you do is just write your business logic, and that's all you need to do. So that's one powerful construct. The other powerful construct from this is you have these core components which are providing you clean, real-time feeds of information. So if you're a quant, needing a clean feed of real-time order data for some purpose, be it portfolio optimization or looking for some kind of signal, you don't need to worry about the business logic of taking your raw order stream and generating some kind of order state. So those are two kind of constructs that we had that people wanted to latch onto, and you very quickly got into a situation where other developers wanted to write these nodes. The challenge there, as most of us probably know, is Q has a very steep learning curve. And you've got developers who are typically writing Python, Java, C++, trying to pick up Q on the side to write one of these components is not particularly productive. So that's one of the main challenge there. And we've tried to overcome that in a number of ways over the last few years. Trying to write very simple DSLs, which meant that all you have to do is write some config to get one of these nodes running. The challenge there is as soon as you want to do something interesting, you need to write some Q code. It's unavoidable. The other approach we took was kind of rewrite our libraries to do the publish subscribe components in a native library like C++ and provide Python bindings. So then you can write code in what you're familiar with. The challenge there was you end up duplicating your code. You can't take one of these modules and just import it and just have a single copy of the code and a single set of tests. You need to replicate it across. And the other thing was a lot of our developers generally like to write Python. If you're writing native Python, doing high-performance Python is not really a thing in native Python. You need to use something else. So those are kind of two challenges that we had with this approach. So once KX announced PyKX, we were super excited because that kind of unlocked this whole world. So what we could do there is just take our existing libraries and wrap it up into as PyKX with PyKX bindings, make it available to anyone who wants to write Python straight away, just to work in Python code with some simple wrappers on top, and they can create one of these nodes. That was kind of the potential of it. And once you do these leaf nodes, you can take it one step further and also just replace your core nodes. The key benefit there is, for something very simple like a reference price engine, that logic, anyone can take a look at that and identify bugs or make small changes to it to address changes in how you want the logic to be applied. So that's the other key power there. There were some challenges there, however, with how PyX is implemented, in the sense that it's more it's written in a way that it's meant to be used as a library to pull data from KDB. It isn't necessarily written in a way that allows you to integrate it in this way. So I hand over to Oliver to run you through some more technical detail of what we had to overcome to get it to work in this way.
Okay, so yeah, using KDB for real-time event processing. As Mohammed mentioned, KDB or PyKX natively acts much like a getter to KDB. You can make a synchronous call to KDB, whether that's the embedded process or another one. You get the result back. What it isn't so great at is asynchronous handling of data coming in, publishing data, accepting connections. So using that, we had a few goals we wanted to solve with PyKX. First and foremost, we need to solve business requirements without requiring KDB expertise. This is the #1 goal. If we can't achieve this, that we can't say the project as a whole has been successful. Secondly, we want to integrate it with the existing Q framework. First and foremost, this is to leverage the existing pub/sub framework, which is very robust. And secondly, we want to avoid re-implementing existing features just to avoid duplication of effort and to make sure that any changes, we don't have a PyKX and native KDB coming out of sync. The third goal was performance to be closer to KDB than to Python. And finally, as a long term, we want it to eventually become the next generation interface between Python and QF. So firstly, I'll just go over the PyKX internals briefly. For those who are unfamiliar with it. So PyKX itself is just a module you can import into a Python session. KDB Plus runs embedded inside Python, and Python controls the program flow. Very crucially to this, the KDB event loop does not run, and this is the source of the out-of-the-box behavior. So PyKX interacts with the embedded KDB via a shared object titled libq.so, and this is essentially a compiled version of the C API that's public with a couple of enhancements. There are probably actually a few interesting things you can do with libq.so that you can't do with the API, but that's probably a story for a different time. Python and KDB functions are completely interoperable, although you won't be able to serialize a Python function to go over the wire. Finally, KDB objects in Python can be converted to a number of formats, probably most of the ones that people are familiar with. So going back to the event loop, not having this causes a few issues that we really need to solve. As Mohammed mentioned, we want to insert PyKX CEPs into the middle of the graph. This means not acting only as a client, but also acting as a server. So we need to be able to accept connections, we need to be able to stream data in, we need to publish data out asynchronously, and finally we want to run timer events. So we've implemented this essentially using Python ASIO, as well as some other enhancements. The main one there is the introduction of a proxy thread. The proxy thread main use is to accept connections. So PyKX isn't able to receive incoming connections on its own. Instead, what we do, we have this proxy thread. Python itself will listen as a TCP host and UTS servers. So clients can connect to that. At the same time, we have the proxy thread, and when we receive an incoming connection in the callback, we invoke the embedded KDB to connect to this proxy. And this allows the embedded PyKX to actually recognize this connection. Once you've done that, the proxy takes control of the client socket, and then it essentially just echoes messages back and forth. And I'll go into this in a bit more detail. For socket operations itself, again, we have Python put a reader on the socket, and when we have an incoming message, we invoke KDB to drain the socket. If we get a synchronous message, since KDB draining will block until async, the proxy actually follows that up with an asynchronous message that just does nothing. Finally, after any KDB operation, we always flush all handles. And to prevent slow consumers from blocking here, the proxy will handle all the buffering there. Finally, timer events themselves are pretty straightforward. We just have a thread in Python that sleeps and periodically runs the KDB timer function. So a bit more detail on accepting connections. So as I mentioned, Python listens with TCP and UDS servers. At the same time, we have the proxy thread also operating as a UDS server. And this is mimicking the standard KDB format so that the embedded KDB can make connections to it. We have this outside of the normal socket port range so that KDB, or it won't conflict with any KDB ports. So when we do receive an incoming connection, client handles authentication, assuming it succeeds. It then calls the embedded KDB session to open a connection to the proxy. After doing so, it passes the client file descriptor. At this point, the Python will disconnect itself from the socket, and the C++ proxy will take it over. And then it will run the handshake, whether that's the standard KDB IPC handshake or a WebSocket TLS. And for WebSocket and TLS, the proxy will handle either the WebSocket serialization or encryption. So I guess, how does this actually perform? Since we've got a bit of a Rube Goldberg machine going on. So benchmarking it, there's a definite impact that's dependent on the message size, or rather it's fixed for the message size, so smaller messages, it's more significant. So we can see with small messages, we're at about a third of the performance of native KDB, but with larger messages, we're pretty close to native, around 80% of the performance. But this is purely socket bandwidth. So how does this actually perform in a real setting? So here I've got an example CEP. This is a real CEP that we have in production, and the point of this is to calculate contributions to the volatility surface. So the reason we use this is originally implemented in Python. As data volumes grew, Python was no longer able to keep up and it was rewritten in Q. So this gives us, as a point of the benchmark, we have 2 points of comparison, both to KDB and to Python. The logic per update is somewhat complex. It's about 30 lines of Q, quite terse, has a lot of joins, a number of updates on different keys, upserts, and some lookups. So the latency here, there's a bit of a fixed penalty. It grows slightly at the very high percentiles. This is largely due to garbage collection in Python and could probably be tuned to clean that up. And the CPU usage, again, a fair bit higher, but easily able to keep up, and certainly much better than the native Python performance. As I mentioned originally, our first goal is to allow users to use PyKX without needing to be familiar with KDB. So here we've got 3 examples, all of the same QSQL query, which is just calculating a VWAP. So Q, probably most people in this room are familiar with. PyKX, if you look at it, it's quite similar. You still got in the strings some KDB syntax. You've got the quantity, average price. You need to know the inline notation here. Likewise with sim, the sim lookup, and symbols. So what we're doing here is we're introducing a new class, which we've called col, as part of QF. And this class essentially has all of the relevant functions built in as methods. Plus we have some overloads on things like equality, so that these will essentially build into a KDB parse tree when it goes into the select statement. The advantage of this is that we can provide these methods and the IDE will hint them. So users don't need to be familiar with KDB syntax, and the standard library, or at least the relevant parts of it, are all available as hints from the IDE. They don't need to be familiar or go and look up kx.com. It also handles, for more complex things, things like enlisting symbols and that sort of thing that non-KDB experts are probably going to be caught up in. Hopefully this is visible to the audience, but here is an example of the Notional service that Mohammed had in his slides. So we're leveraging the Q framework internals here. Just importing QF essentially does all of that. So there's minimal boilerplate here. All you need to do, we can just invoke the subscription functions that already exist. This will handle everything important, getting data, streaming, and all we need to do here is include the business logic so I can fit the entire CP into one slide. So here the logic itself is quite straightforward. All we're doing is joining and then a single update column, just multiplying the price and the quantity. But there's essentially about 2 lines of boilerplate that actually consists for this CEP, and the rest is all business logic. So how we're actually using it, as I mentioned at the start, we had 4 main goals. First and foremost is that it had to be usable by non-KDB experts. So we've actually got traders, quant researchers, and software engineers proficient in other languages, all currently using PyKX. For CEPs that actually fit into the graph, we have software engineers and KDB developers doing this with PyKX. Performance is acceptable for the majority of our CEPs. There are a couple where we'll need some performance tuning for it to be usable, but for the large majority, it's very usable. One free win we actually did find is that we've been able to, in a couple of cases where we would otherwise needed to have written a C++ plugin to extend KDB somehow, we've actually been able to write a PyKX CEP instead, and this has allowed us to deliver features much more quickly. So what's coming next? We're going to keep rolling out more lines of business, expand the use cases. We're still looking into performance tuning. And KX actually has some new features coming in 1.6 that will make a lot of what we've done easier and hopefully more performant, but I won't steal their thunder. Speaking of KX, I'd like to thank the entire PyKX team, especially Kian Shepherd, Bruno Lahjarik, and Connor McCarthy, who've helped us personally with our journey. And any questions from the audience, if you have any? Yeah?
Your proxy thread, are you just invoking the Q IPC callbacks?
So we drain the socket manually in Q, which doesn't invoke the callback, but then we'll essentially run the callback code when we do that.
About embedded KDB with any limitation in terms of memory, like licensing?
Licensing at the moment, you need a separate license for PyKX. If it's being open source, that might change, but I don't want to speak on behalf of KX here.
But you have 64 like bit, right?
Yeah. It works with a normal 64-bit. All right, I'll open up for the next speaker.